Today I'll talk to you about first ethanol. Ethanol has been booming. Earlier, of course, ethanol had many applications, no doubt, and one of those big ones is, of course, for production of alcoholic drinks, and that's been something that has been going on and on, up and up. But since the last 15 years, I'll say, there has been a surge of interest in ethanol used in blend with petrol, as you know, and so that has led to a massive rise in the consumption of ethanol. There are a few other areas where ethanol is very important. One is really to make plastics. The largest volume plastic is polyethylene, which comes from petrochemical sources. But there is an increasing realization that it is not sustainable for various reasons. One of those is the fact that the feedstock is a petrochemical. Okay, so people have been looking at alternative resources, yeah, and that's where again ethanol becomes important. And I'll show you a couple of plastics which are really based on ethanol. The other, of course, in the last 2 years, there has been a massive surge in the area of hand sanitizers. Disinfection has been a huge area. Of course, this is not going to last. I'm sure it's going to peak and again come down, because I hope that everything will finally fall back to normal. And it's also not a good thing. Every time rubbing your hands with alcohol, and all that alcohol is actually going into the atmosphere. Nobody is talking about that and what kind of pollution is being created for these massive amounts of alcohol. And you look at the population, look at the billions of people in the world, and there's nothing else. It will just have to go into the atmosphere. Ethanol has many different feedstock, and you'll find it varies from country to country. Like, for example, the largest producer, United States, they use coarse grains. They use maize, things like that to make their alcohol. All right. Whereas very big countries like Brazil and India, they mainly produce it from sugarcane. In fact, a large number of people produce it from sugarcane. Sugarcane is also differentiated from molasses, and I'll tell you exactly why that distinction is made here. And then a lot of rotten crops which have got spoiled, and really this would be one of the best things to do. That why not just convert it into ethanol, okay, or biogas. So those would be the kinds of uses of things which have begun to rot. But the real big breakthrough, which is, I will not say that it has come. I think that there's a lot more work that needs to be done, is really to be able to take lignocellulosic biomass. Every time you harvest some crops, all the rest of the plant parts, which is all lignocellulosic, you can see what's happening in Haryana, for example. Every time they'll burn it, and it creates massive amounts of smoke. And why are they burning it? Because people have not really been able to find a good way of using it. Although, there are very simple things you can do. You can actually have a baling machine and bale it up and into a very compact form, which can then be taken, you can burn it in a boiler, or you can make alcohol out of it by hydrolyzing the cellulose to sugar. So that would be nice, and that is in fact one of the very important areas. In our country, there's another important opportunity which actually we had introduced a few years back, but hasn't really taken off yet. But I hope sometime in the future it might be big, which is that you can grow a lot of seaweed, because we have a long coastline, because those are really polysaccharides, the substance in the seaweed, and which can be hydrolyzed. You can get galactose and sugars like that, which you might be able to again use for making ethanol. So the scenario might change in the next 30 years. And in any case, it's a stopgap measure, because if the vehicles finally become electric vehicles, then of course none of these things will be required. But I think that over the next at least 20 years, this will be very much there. I just don't see electric vehicles coming in such a big way, at least not in 20 years' time. It will come into some urban areas, relatively more wealthy cities like Bombay. Yeah, there'll be people who will drive electric vehicles, but the bulk of it is not necessarily going to happen so easily. And even if it happens, that electricity is really being generated by burning coal. So while it looks very pretty, you don't really see the ugly side of it. It's just that the pollution has got shifted somewhere else. That's all. I mean, otherwise it's there. Unless you can generate electricity by some other means in that massive amount, it's not going to really help. Certainly, it's not going to help the climate. Okay, now let's look at the origin of use of ethanol as a fuel. And it actually goes back to the time of Henry Ford. When he ran his first vehicle, this is the vehicle, in 1896, it was run with ethanol. This petrol, etc., came later. After that, this whole petrochemical industry boomed. But originally, that's the way it was done. And the people who were very visionary was the country was Brazil. Way back, in fact, in the 30s, they actually started putting a bit of ethanol into their cars. The reason was because Brazil was had a huge land area, and they were very big in sugarcane cultivation for a long time. And so Brazil were the leaders in sugarcane. I mean, India, of course, is the other country. For a long time, they were using small amounts. This slide was actually shared with me by the people who are the pioneers of the present day Brazilian ethanol industry. Around 1970s, when there was a big crisis of petrol and diesel and all, that it surged. In fact, today, I think he just sent me a mail that they're using about, on an average, about maybe around 20%. And all their vehicles. It's not that some vehicles run only on petrol. So it's about 20-25% in Brazil, and in the US, it's about 10%. India is also making very rapid progress in this area, and they're introducing some blend. Like today, it's about 5% is typically the amount that is put. You as chemical engineers should actually ask, what do I gain from putting ethanol into this? In fact, some of the data is very dubious. Like, for example, you find that the mileage variations are within 5%. So what did I gain? Did I gain in terms of reduced emission, self-reliant, and using less of petrol? Yes, that's good, provided, of course, it's translating into a very tangible benefit. That is, there should be no loss in the mileage. The emission should come down. Then it will be important. Now, this is the fairly recent. In fact, I just took it out day before yesterday while preparing the lecture. 2020 by country. It's really changed a lot. I mean, in fact, Brazil was the number one. They have now become second, and it is the United States which is now consuming. This is in million gallons. Million gallons means this will be about around 56 billion liters of ethanol, which is now being used in the United States, which is large, and so is Brazil, of course. The others are Europe has more of diesel vehicles, and we'll talk about that. So they have less consumption. China, India, actually these were negligible. Now at least it's quite prominent. So you can just see, and these are the major countries which are going for ethanol in a big way. Uh, I'm not going to pass judgment yet on whether it's a good thing or a bad thing. There are issues. Like for example, if you're deriving it from sugarcane, and if you look at the amount of water and fertilizers which is consumed in cultivating sugarcane, and if you look at, what are the potential negative impacts of that, it can be massive. The wisdom of these things one will have to look at. I mean, it's okay. We're looking at the technical aspects of producing it, but wisdom is different. So you'll have to, at some point, of course, analyze for yourself whether in the long run this is really sustainable or not. Did you have a question?
So is
What?
ethanol a byproduct?
Ethanol byproduct? No,
Yes,
in
sir,
fact,
of
that's a
sugar
good.
production.
Yeah, yeah, that's a very good question. I'll come to that. Just hold on for a minute.
Thank
I'll come to that. That's a very good question, and make sure that I answer it. Another very important thing is plastic. Huge amounts of plastic are produced, and there is more we talk about how much we are damaging the environment and all. In reality, what you see is that the consumption of plastic is just shooting up, and all in the guise of something or the other. When we were kids, there was no plastic pouches in which you got your milk. The milkman came and poured some milk into your button. That's not what you have today. Everybody has a pouch of. Yeah. Look at all the packaging. Look at Amazon, all these things. Every time you have something delivered, how much packaging is involved? And it's just massive, the amount of plastic that has been created in the plastic bags, this, that, name it. There are very good things about plastic. Let's not undermine that, but it's also a huge problem. So for example, the two things that people have been wondering about plastics, and in case you want to make it more sustainable, recognizing that plastic has got merits. It is not all bad. There are many good things about plastic, like a plastic bucket. Or when I think of the women who travel a few kilometers carrying water on their head, and they use that plastic jar, which is about 10, 12 liters. If that had been heavy, they would be in big trouble carrying it, because it is lightweight. It's a bit easier for them to carry. So there are, or a bucket, a plastic bucket. It's so convenient. It's not every day that you're changing your bucket. You have your bucket for sometimes years together in the at home. Right? So there are dustbins, plastic bins. They're all very useful. So that's there. But the two things which I think would be important to consider, one is that almost all the plastic is derived from petrochemicals, and the largest one, which is polythene, is basically just a polymer of ethylene. It's coming from the cracking of hydrocarbons that you're getting your ethylene. It wasn't always like that, and I'll come to that. And so there is an increasing trend. This is the data from 2011, but this is actually going up. What you'll see is that there are these kinds of polyester PET bottles and polyethylene. One is, of course, that I can recycle them. That should be done. But if you look at the data on recycle, it's negligible. And where has all that got put in? It's being dumped into the seas, the oceans. And there are massive ships which take, a shipload worth of plastic and just dump it into the ocean. The damage that we have created is unbelievable. I don't know how one can be proud of that kind of a development. And the other is, of course, trying to make it from bioresources. So these are bio-based plastics. They're not different from the conventional PET bottles or the conventional polyethylene or the conventional polyamide plastic. It's only that you're producing it from a bioresource. And I'll show you one example of how you do it. These things, people have now started calling as bioplastics. The meaning of bioplastics earlier was different. Bioplastics meant biodegradable plastics. These people have hijacked the agenda and have started calling bio-derived plastics, which are non-biodegradable, as bioplastics and fooling everyone. It's not biodegradable just because it's a bioplastic. But the real biodegradable plastics are these. Now, that's also very interesting. You can actually make a biodegradable plastic from a completely synthetic feedstock, like for example, polybutylene succinate. It's derived from petrochemicals, or even polybutylene adipate coterephthalate. These are derived from synthetic processes, okay, and using synthetic material, but they're biodegradable. So you can see, I mean, this is from a bioresource, non-biodegradable, from a petrochemical resource, but biodegradable. And then, of course, you have got what you would call the most ideal situation, which is things which are derived from a bioresource and are also biodegradable. Like, for example, polylactic acid, polyhydroxy butyrate or valerate. Okay, there are fermentation processes by which these can be made. Now, these are generally much costlier than your standard plastics, and also nobody has been able to produce them in such high volumes. So they are niche areas, like you have some fancy fragrance bottle or something where in any case you can pay through your nose or things like that. So the bottle is made with some fancy biodegradable packaging. That's okay. But if I have to do that with my pouch of milk, where milk itself costs me about 15, 20, 30 rupees. And if the packaging itself is going to be 30 rupees, nobody's going to buy it. Yeah? So obviously one will have to look at these kinds of issues. But certainly this would be the most ideal situation. Like for example, nursery bags. There's so much of plastic in nursery bags. And then finally you're putting it into the soil, those bags with a small plant and soil and all that. And it would be wonderful if that bag degrades. You don't want that bag sitting in the soil and being non-biodegradable. So these kinds of bags made from polylactic acid, they are different types of plastic, are becoming increasingly important. Now, this is very interesting. You would have seen polyethylene. If you take ethanol and you dehydrate ethanol, what will you get? You'll get ethylene, right?
Yes, sir.
Yeah. And in fact, it is so amazing how things come around a full cycle. I joined a company in 1985 after I came back from the US, and it was ICI, the people who invented polyethylene. In India, they had set up the first polyethylene plant, and when I joined, I remember seeing that plant. 85 or 86, I had visited the plant in Risha, and it was based on ethanol, the polyethylene. And what a tragedy that plant had to shut down because in the late 80s, people started introducing polyethylene from ethylene made from petrochemicals. And in those days, it was not very costly. And so, cracking of this, and people would brag about, how you make polyethylene and all. Okay. And look at these pioneers making it in a perfectly sustainable way, and it's closed. They have to sell that plant for almost a pittance, something like, I think, some 14 crores or something, big plant. And today, is coming back a full cycle after what? After about 30 years. So many of the things that may have been good practices in the past, which got abandoned, you don't be surprised if they come back. Why were they interested? Because India had so much sugarcane. And so ethanol production was there. In those days, people didn't drink like crazy. There was a lot of ethanol, which was, and neither was the consumption of plastic so much. I mean, it was there, but it wasn't so huge. And so things like your buckets, and those are the things that became very popular, plastic buckets and stuff like that in those days. So what were they doing? Now, this conversion of ethanol to ethylene, the dehydration is a endothermic reaction. It requires substantial amount of energy. So that's one of the things that you have to note. So what they do is that they feed ethanol, and alumina, acidic alumina, is taken as the solid state catalyst. So you have a bed of alumina catalyst. In fact, you have two such fixed beds of the catalyst. And because it's endothermic, so you heat it externally with natural gas or coal or whatever. It's of course very nice that you're getting ethylene and polyethylene, but don't forget, I require energy. And if I'm burning my energy from a fossil fuel, then I have to ask myself, was I not better off using petrol? Why would I do this? Of course, I'm talking about making polyethylene, not ethanol. The sustainability things you have to look at very carefully. And you must always forget about only this particular lecture across the board in anything that you have been taught. You ask, where is it ending up finally? Where is it going? And where did it come from? And you start estimating the entire chain of events. What was the actual feedstock that you started with? It's like Haber's process. I can say, hey, it is nitrogen and hydrogen going to ammonia, and I can feel great about it. Or I can say, no, it's not that. It is basically natural gas plus water plus air going to ammonia, because I'm deriving the nitrogen from my air. I'm deriving the hydrogen from my natural gas, and my water is being required for my steam reforming process. So it depends on how you look at the problem. Everybody is talking about sustainability, but they're talking of it from a very, very limited perspective. I am running an electric car. I'm so happy about it. What the hell do I care where that electricity came from? So those are the kinds of issues that you need to look at. Anyway, then of course you dehydrate, but all of the ethanol is not converted into ethylene. So you need to do a purification. And so what you do is now you put it in water. So the ethanol goes into water, and your ethanol, which is not soluble, is coming out from here. You can actually do a conversion. What is the yield based on ethylene and 100,000 kg per hour? So it's not bad. But there'll be a small amount of ethanol which ends up in your water. You may actually then concentrate that ethanol and then put it back over here. As I told you, the first plant in India was based on this technology. You can imagine that if people are talking about sustainability and polyethylene as a made from Bioresource, then it will be very, very interesting to look at ethanol. By the way, I'll just ask you to think about it. You don't even have to answer it, now. But there will always be people who will try to cheat. Like, for example, how do you prove that you made polyethylene from a petrochemical ethylene or from a ethanol ethylene? Suppose if somebody is giving a subsidy for a polyethylene which is obtained from ethanol. I'm just taking a hypothetical situation, but how will I prove that I've made it from bio-derived ethylene? So just think about it. If you come up with the answer, I'll be very happy. This is another, I told you about polylactic acid, that this is another very important polymer which is coming into play. And sometimes it's not just polylactic acid, it could be that it's an ethyl lactate. So you may have to actually react it and introduce an ethyl group. Again, there could be a reaction with ethanol because that's how you get ethyl lactate. So ethanol can come twice over. How would I make lactic acid from ethanol? Well, the first step is you can oxidize it over a silver catalyst. That's what is done here. We'll be discussing silver catalyst when we talk about ethylene oxide. This is what industrial engineering and chemistry is all about. That these subtle things that you do, manipulating processes, changing temperatures, this, that, little bit here and there, and instead of forming one product, I form another product. Instead of forming ethylene oxide, I end up with acetaldehyde. Both are oxidation products. They're isomeric, but they're so different in their properties. This is the process for making acetaldehyde. So you have to heat it. There's an oxidation, so obviously you need to flow air and alcohol together. In many cases, this is another lesson which all of you should learn, and I find that this mistake is made by numerous people. People are obsessed with conversion. That I took ethanol and my conversion is 100%. Conversion means nothing. Conversion only means that how much of raw material I had and how much of it I consume. But what did I make out of it? Did I make all of the desired product out of it? Or did I make some desired product and some undesired product? So many times what you'll find is that actually it's smart to not convert everything. Just stick to the place where you have maximum selectivity. Get your desired product and then you try and see if you can recycle the unreacted part. That is much smarter thing to do rather than converting it into some rubbish. So that's what these people do. They work at a conversion of 50 to 70%. Why? Because at that point, they get a very high selectivity, something like 99% of acetaldehyde. But then what happens is that if you just let it sit, obviously your acetaldehyde can also get oxidized. So you don't want that. So you want to minimize the amount of time that your product is being exposed along with your reactant. So that's what you are able to do when you are able to, let's say, convert it 50 to 70%. Maybe it happens in a very rapid rate, and after that it slows down. So keep that also in mind. So after that, basically you'll get your acetaldehyde, and acetaldehyde is volatile. So you can actually distill it over, and you'll get your acetaldehyde from here. And then your unreacted ethanol, you might put it in water in this, and then later on you can again recycle your unreacted ethanol. And the reason for that is because I might form some side products, etc. So I need to give it a wash with water. When I give a wash with water, my acetaldehyde is also soluble in water. So is my ethanol. So they will remain in water. All the rest of the insolubles will go as exhaust gas from here. And then what I do is that I distill over my acetaldehyde in this column, and then I'm left with the ethanol water concentrate, which I just recycle back. So that's the process. Now after that, this is, by the way, not a great chemistry, and this is one of those where introducing a bioprocess, bioconversion would be much better. Okay, and then these exist. I'm not going to discuss it, but then you can take acetaldehyde, react it with HCN. It'll add the HCN across the CHO, and you'll end up with lactonitrile, and you hydrolyze the nitrile group to a carboxylic acid. So this is your OH coming from addition of HCN, and the CO2H is coming from the hydrolysis of the CN group, and you end up with lactic acid. Now, this is another thing. This particular lactic acid which you get is a racemic lactic acid. Now, you have to take a call that do I need a chiral lactic acid, or is a racemic lactic acid good enough for making the polymer? If you find that, yeah, it's okay. I mean, it is not a huge difference in properties, whether I use a chiral lactic acid or a racemic lactic acid, then I'm not going to make a chiral lactic acid. But on the other hand, if I'm using lactic acid to make a pharmaceutical product and I need it in optically pure form, of course, then I'll try and use a chiral lactic acid. But for these plastics, it may not be so critical. And so I might actually do this. Only thing is I'm using HCN, not the best thing to do. Always, there will be some things which is, you can say there is a room for improvement. And you may focus on that and say, I'm just going to work on this part. And I try to do the conversion of acetaldehyde to lactic acid in a different way. I focus on that and I can work hard. I may not achieve the objective, but if I do, that's a great thing. So that's how you choose research. All this is, of course, coming from where? It's coming from ethanol, the two that I showed you. So we must know how ethanol is produced. And as one of you very, very correctly said, you can look at it as a byproduct of sugar industry. The question is it? And I'll explain to you as I go along. What do I do when I make sugar from sugarcane? First, of course, you crush the cane and you get the juice, and you get about 700 kg of juice from 1 ton of cane. You get a bagasse as the insoluble, the lignocellulosic mass, and all these people feel very happy that they are one of the green technologies, because they burn their bagasse to generate the heat that I need to strip off water. What else do I need in sugar production? Is basically all about evaporate, evaporate, evaporate. I have to keep evaporating, then come to the crystallization point, which is around 60% sugar. You're starting with something like about maybe 12 to 15%. So lot of water has to be evaporated, and you use the bagasse for that. But on the other hand, if you could do clever things, let's say where you did not have to do the evaporation by some smart method, it could be doing reverse osmosis of sugarcane juice. I can do dewatering. That would be nice. It may be a much lower energy option than thermally heating. And then, I can use my bagasse for all kinds of different uses. It's a very nice raw material for making all kinds of plates and cutlery and things like that, or goes into paper making. So I can use it. So if I didn't burn it all up, I would have uses of bagasse. And what you do is that finally you get sugar. Okay, and sugar is not just taken out in one crop, it's taken out in several crops. So you get a first crop, then again you take the mother liquor after filtration, again you heat it, again you'll get a second crop. Obviously, progressively the quality of the sugar will deteriorate to some extent. It may have more color, it may have some side products. So you make different grades of sugar. Now, each time you're doing this, the mother liquor that you're getting, that is known as molasses. So I take out one crop of sugar and I get the mother liquor. Obviously, the mother liquor still has a lot of sugar in it, and it's called B molasses. Then I again heat it, I evaporate, and I take out some more sugar. And now I'm left with another mother liquor, which is like, you can say it's the end mother liquor. That means after that, you cannot crystallize out any more sugar. Doesn't mean sugar is not there, it's there, but you cannot crystallize it out. And that is what is known as C molasses. And that's what our country was using until 3-4 years back as the only raw material for making ethanol. And how much do you get? You get about 40 to 45 kg of that per ton of cane, so limited amount. And as you said very, very rightly, absolutely. If this is what you're going to do, then yes, you are making it from the byproduct. And maybe molasses doesn't have that much of applications. Also, that's not true. It's used in cattle feed and other things, but still you don't feel so bad about converting molasses into ethanol.
So in this case, you said that there is a C molasses beyond which we cannot extract any more sugar.
Right.
So in the case of nitric acid as well, we were getting a formation of 69%, and then we were using a dehydrating agent. So can we do anything in this case to?
Absolutely brilliant. You cannot do it by this crystallization process, but you can actually do it by solvent extraction. You can actually take out the sugar. Now, what happened is that because I also need the molasses, you will always try and do the easiest thing to do. And you must. So, if, for example, getting value out of the molasses in producing ethanol, and ethanol also costs a lot of money, then I might say, hey, I'll forego that 15-20% which is left behind. You understood?
Yes, sir. So for making ethanol from molasses,
Yeah.
so is there a certain grade of molasses that we require?
Well, you can do it either with B molasses or C molasses. And I'll
Understood.
come to the ethanol production. Before we actually take out sugar, and I might have given you a very simplistic view. I said evaporate, evaporate, evaporate. Actually, it's a complex operation. It's not as simple as you think it is. And there are many pitfalls. So let us try and understand what are some of those. Like, for example, when I'm crushing, when I'm getting sugarcane juice out, and by the way, we make it from sugarcane, and Europe, all of Europe actually uses sugar beet. That's how they get their juice. Now, what happens is that this is especially true about sugar beet, that if you do not control the pH in the extraction process, then some of the pectin, which is present in your, let's say, sugar beet, can get released, and that can affect the crystallization process. So, what you do is that it's quite common to pass sulfur dioxide. By the way, sulfur dioxide has uses, it's not just for making SO3. And so, sulfurous acid is an important thing to incorporate into sugarcane juice, mainly as a way of controlling the pH. You don't want to completely acidify it, because your sucrose is a disaccharide sugar. It will get hydrolyzed. So it's a very tricky operation that I don't want to hydrolyze my sucrose, because sucrose is what I consume as sugar. But at the same time, I don't want all this pectin. So that's also important. Then, in fact, another thing is that many times the juice, of course, when we are making ethanol, we are reacting it with yeast, and then it's fermenting to ethanol. But that's not the only fermentation process that can happen with ethanol. Ethanol can be degraded by bacteria and fungus, and it can form things like lactic acid, which will cause a problem. And so, what you have to do is then make sure that none of these microbes get into your system. Okay? So, one is, of course, thermally to sterilize. The other is that this sulfur dioxide actually acts as a biocide, and it prevents the growth of microbes. And the third is that it's very important. You see, when I crush the cane and I take out the juice, it's not only sugars. There are also some proteinaceous material, amino acids, etc., which are there present in the juice, which also get into your system. And when you are heating at high temperature, you can have what is known as the Maillard reaction. It's a reaction between your amino groups and your carbonyl. That again can lead to a color formation which you may not want, in case if you want white sugar. So the sulfur dioxide actually helps to block the color formation. So sometimes, the way you kill several birds with one stone is quite amazing. By the way, let me also tell you this, that the production of sugar was one of the earliest industries. chemical engineering industries. And all these things today that we talk about, multiple effect, evaporator, this, that, actually had its origin in making sugar. And they realized that if they have to just evaporate so much of water, that it takes a huge amount of energy. And then they developed this process of recondensing that water and again recycling the heat that is evolved. And so that is the birth of multiple effect evaporator, which is such a fundamental thing. So look at these things also from a historical perspective. They're very, very important, all of these processes. Okay, now comes the question. So if, let's say, I make C molasses, and as I told you, till middle of 2018, that's all we used to do. And this is a typical composition of molasses. Very complicated, very dense. 1.43 is the specific gravity, and it's a combination of organics and inorganics. You have both fermentable sugars, you have unfermentable sugars, and then when you are actually producing sugars, and even from the process of in your sugarcane juice, there are trace amounts of organic acids. And if you analyze sugarcane juice, you will find that it's very rich in things like potassium. So these are the inorganics, and you can see total inorganics is about 10%, very high. So this is also very important to note that when you are going to do a fermentation, of this molasses, sometimes if you have too much of these salts, the bugs will not work. You may have all the sugars, and that's one of the reasons why the molasses has to be diluted. So you have to dilute it by about 3 to 4 times, okay? And so that your salts are brought within an acceptable level, okay? And then you can do the fermentation nicely. Another very, very important thing to remember is, as I told you, if I'm interested in sucrose, I don't want my juice, the sucrose, to get converted into the monosaccharides. I want it to remain as sucrose. But there is always this inversion process which is possible, which is that the disaccharide gets hydrolyzed to monosaccharide. Now, this is also very interesting. Like, for example, I was asking the people in Brazil that for the fermentation to ethanol, is it necessary to hydrolyze the sugars into monosaccharides, or can I just use this? And they said, yeah, you can use it, or even if it gets hydrolyzed to monosaccharide, in fact, if it's anything, it's better, not worse. So many times, all these jugglery that you have to do to make sure that you are not converting the disaccharides into monosaccharides may not be so crucial when you're making ethanol. And I was actually asking myself, why can't I evaporate sugarcane juice the same way that we evaporate seawater and make salt? What are you doing? You're using solar energy there. Why does this have to be done in a factory? I'm sure there are many, many valid reasons, but it should not prevent you from asking the question, because I can save so much energy if I can do that. Maybe what will happen is all these bugs and microbes, etc., will attack. But I can say, no, I will put some biocide so that they don't grow. And so I can play, do all kinds of tricks. Now the question is, coming back to your question, what decision was taken in 2018? You can see July 27, 2018. What did they decide? Government allows mills to make ethanol directly from sugarcane juice and bee molasses. And they are pushing it more and more. Okay? In fact, they're giving you a subsidy if you produce ethanol. And the concern that you have to look at is that obviously I'm diverting sugarcane juice from sugar production into making ethanol. Now I'm no longer talking about the byproduct. Now I can understand if someone says, no, there's a glut of sugarcane in our country. There's so much sugarcane we don't know what to do. And therefore, I have no choice. I'm just making ethanol out of it. Really? If that were the case, don't cultivate so much sugarcane, because sugarcane is one of the most water intensive crops. It takes so much of fertilizer. Okay, so you have to think hard. Is that the wisest thing to do? I'm not saying that it is not the wisest thing to do, but you should engage yourself in these kinds of debates and discussions. Then it becomes interesting. Not just, don't look at chemical engineering as some just processes. Look at all the way from end to end. Then it becomes interesting. Let us quickly go through the actual process by which molasses is converted into ethanol. Okay, and the same kind of thing will apply also for sugarcane juice. Let me also tell you that there are certain advantages of producing ethanol from sugarcane juice. I'm not going to go into it now. The most important things is that there is an enzyme, invertase, which converts the disaccharides into monosaccharides, and then you have a yeast, zymase, which is what really does the fermentation. It's a exothermic reaction. Over here you can see that you get ethanol and you get carbon dioxide as a byproduct. There are also certain side reactions that take place. One of them is formation of acetaldehyde. Need not be only acetaldehyde, it could be some other aldehydes and some higher alcohols, not ethanol, are also formed. These have to get all removed from your ethanol. So this is the process. As I told you, I mean, because the molasses has also a high amount of inorganic salts, and also because the bugs cannot really work when your molasses is very, very concentrated. You have seen it's a highly viscous material, so you have to thin it down. So that's what is done in the diluter, and a part of it is sterilized, and with that you effectively grow the yeast which you require for your fermentation. So it's also helping in the growth of the yeast. So part of it is diverted here, and most of it goes over here. And you can see from something like about around 40% sugar is diluted to about 10 to 15%. So the fermentation takes place here. You saw that carbon dioxide is a byproduct. So one gets rid of the carbon dioxide over here, or you can use it as a industrial feedstock for some applications. Because it's an exothermic reaction, you need to also cool the tank to maintain the temperature. And then at that point, it will have around 5 to 6% of ethanol. So earlier, I mean, you could also, like for example, people who have beer. Beer typically has about 4 to 5% of ethanol. So you could actually just after that have beer as a product, after the fermentation. Okay? Or if you want to make more concentrated ethanol, then you have to put it into this. You can see it's called a beer still. So effectively, what are you doing? You're distilling, because ethanol is more readily evaporated or boiled than water. So what comes out, the distillate, will have some of that byproduct aldehyde and things like that, which I mentioned. Plus, now the alcohol might get concentrated to something like 50 to 60%. And what you get over here is the rest of the mass, which is known as slops, or it's also referred to as spent wash or vinasse. Now, this has always been a huge problem for the industry. Now what they do is they recover biogas from this, but even after that, they're not allowed to just discharge it. So what they have to do is that they have to actually evaporate it to dryness, and then they have to incinerate it to have a satisfactory solution to the problem. In Brazil, they actually put it back into the sugarcane fields. But for whatever reason, it's still not permitted in India. So they are being forced to evaporate and incinerate, and they all complain about this. What should we do? So in fact, one of the things that is been possible to do is that you can do a forward osmosis between this and this, and you can suck out water from here and put it here, because you need pure water also to as a diluter. So you can actually serve both the purposes. You can get your water to dilute the molasses, and you can also concentrate and thereby reduce the evaporation load on slops.
So can you please repeat this point, sir, for the slops?
Yeah, so the slops is considered to be a waste after you have distilled off almost all of the alcohol. But this always will have some organics. It will have some of the organic acids, it will have unreacted sugars, and all of the inorganics will all be present here. So what people are doing now is that they recover biogas. So as much of the organics as possible, they convert into biogas, and that's a great thing that they do. After that, what you get is called biomethanated spent wash, and that they are not allowed to discharge. And it's the volume is still very large, because you are talking about something like 1/3 or maybe 2/3 of the total volume from your fermenter ends up here. So what has been done now through a project where the osmotic pressure of this is much lower than of molasses. Molasses is a much higher osmotic pressure, about 160 bar. So it's been possible to take these two, this one and this one, through a forward osmosis module, where you pass the slops as feed and you pass this as draw as an osmotic agent. And so it sucks out water from the slops, and the molasses gets appropriately diluted by about 2 to 3 times, so that you straight away get this. And this now gets dewatered partly, maybe about you can do about a 20 to 30% dewatering of the slops. And so to that extent, you can reduce the evaporation load to convert it into dryness and thereafter to incinerate. What they found is that when the water permeates into the molasses, that its behavior is the same as if you take just pure water and put it into the molasses. There's no difference. And so the fermentation efficiency was very good. And so this would be a nice technology to commercialize. And in fact, you can see we would like to discuss the next steps of commercialization. This is the Somaya group. Biggest problem over here is that the membrane modules are very costly, and any membrane process always has a problem of fouling. Your membranes will get coated with molasses and things like that, and whether we will be successful in cleaning it up and keeping it going, that is the big challenge. And as of now, I think the jury is out whether really we'll succeed in doing that. I don't know. You can always find potentially interesting opportunities for doing research. Always try to squeeze out the last bit of opportunity. When you get this, it's also all the aldehydes have distilled over. The aldehydes are more volatile than the alcohol. Then you do a fractional distillation, and then you will get your aldehydes, which might be used as a feedstock in some processes. Once you've taken out the aldehydes, what happens is that the higher alcohols are not very soluble in water, so they will form a separate layer. So you can decant it out, and that's your fusel oil. That's what you get. It's not completely removed, the fusel oil. So you still have to do a rectification again over here. You do a rectification where whatever fusel oil has still remained over here is taken out. Now this is very interesting. Normal boiling point of these higher alcohols is higher than of water or ethanol. But because ethanol and water form a very strong hydrogen bonded system, so those don't distill over so easily, and This is relatively more volatile, the remaining fusel oil. So you get it out and you just feed it back over here, so that gets recycled, and then again it gets decanted, and that's how you ultimately end up removing all of the fusel oil. You're taking off your alcohol from somewhere in the middle of the column, rectification column, because this is more volatile. It comes off, and from the middle you take off your alcohol, okay, and the rest of it, which is almost water, pure water, is coming off at the bottom of the column. You're draining it out because alcohol forms an azeotrope with water at about a 95% concentration. So you cannot get more than 95% pure ethanol over here. So it's about 95%. Now in your vehicle, you cannot use 95% ethanol. It'll corrode the car. So you have to convert it into absolute ethanol. Absolute ethanol is also required for many other applications. May not be so much for like when you're producing alcoholic drinks. No alcoholic drink is 100% ethanol. They will have always some amount of water. So those kinds of things you can probably straight away from here, you can market it. But the rest of it, like for making fuel and things like that, you need to make 100% ethanol. There are also some applications of alcohol where I don't want it to be consumed. So what you might do is add some methylated spirit, methyl alcohol, and then you get what is known as denatured alcohol. It's called a denaturant. All right, and this is not meant to be consumed. But many times what happens is that people actually sell this as illicit liquor, and you will sometimes hear in the newspaper, so many people died consuming illicit hooch, illicit liquor. That's what they did. They actually drank the denatured alcohol, and so that's a problem. Now you can break the azeotrope by putting in a third solvent. Earlier times benzene used to be used, so you can then do a ternary distillation, and that will give you pure ethanol. Or you can also take this 95% ethanol and cook it up with a zeolite like zeolite 3A. You can actually get absolute ethanol by just doing a distillation over zeolite 3A. Or you can also do something known as pervaporation. It's a membrane process where on one side you apply a vacuum. Basically through the membrane, only ethanol, pure ethanol comes out, not the water. So those are the various ways in which you can make absolute ethanol. So that's what you have to do, and this is the process. This is another thing all of you are going to look at, interesting problems to work on. Now, what happens is that making ethanol from molasses, for example, or from sugarcane juice is the easiest. Okay, because I'm already getting the sugar, which can easily be converted into a monosaccharide with invertase, and then all I have to do is fermentation and distillation. So it consumes the least amount of energy. When, like in the US, they are doing it from starch, you can do that, or from a seaweed-based polysaccharide. But obviously, then I have to put in some amount of energy into hydrolyzing my starch, and I have to use an acid because most of the time the starches are not so easy to hydrolyze. So obviously, the level of complexity goes up. Now, if I have to use lignocellulosic biomass, that means all the trash that is left over after I harvest my crops, which today people are burning, you would have seen in Haryana and places. If I want to do that, it's a very, very complicated process. Lignocellulosic biomass is one of the most difficult things to break apart. The very tight bonds between the cellulose and the lignocellulose, and cellulose is also a very crystalline material. Access of reagents to break it apart is very difficult. Huge amount of research is going on in that area in how to prop it apart. So it becomes extremely energy intensive, doing this thing if you want to convert it into glucose, the sugars. What it means is that the technical complexity goes up, as I'm going from, say, sugar to starch to cellulose, but my feedstock would be cheaper naturally if I'm able to use waste lignocellulosic biomass. Obviously, this would go down. So the question is, how do I really strike a balance between these? The rest of the process is well known. It's only about really how to convert the lignocellulosic biomass into free sugar. Anyone who can do that, I can tell you, would be a winner. And there are many different approaches that people are looking at. I'm not discussing those. I'll maybe after this I'll also pass on an email from Brazil where they wanted a joint report with Brazil. And I was thinking, these are the kinds of things some of you could actually be interested in doing. I'll just dig out that email and send it to you. Maybe some of you will get interested. Now, I mentioned to you about molasses. Molasses is not only used to make ethanol. In fact, if you go to a biorefinery like the Sumaya Group, they make all kinds of chemicals by fermentation. One of those very important chemicals that they make is citric acid. You know that you can recover citric acid from oranges or lemon and things like that. But the bulk of it is really synthetic. Synthetic means derived by fermentation from molasses or things like that. So let me quickly tell you, how citric acid, for example, is produced industrially. It's not that small. Of course, this is 2008, very old information. I suspect that it will be maybe about 2 to 2.5 million tons now, the annual production. Citric acid you can produce from, you can use molasses or sugar solution as your carbon source. You can use sugarcane juice directly or molasses. What is very interesting is that the actual development of the citric acid, the metabolite, these are all secondary metabolites, takes place under conditions which are limiting in nitrogen and phosphorus. Let me quickly show you the typical, this is shown for a bacteria, but it would be equally true for many other microbes. Typically, you have several phases. The first phase is a lag phase. That is, you have added everything, but it's like nothing is happening, and it's like an induction period. So that's called the lag phase. After that, it really takes off, the multiplication of the cells. This is known as a log phase. In fact, you can see this plot is logarithmic. So basically, the growth is exponential that takes place. Thereafter, what happens is, for various things, like as I told you, maybe because of this nitrogen and phosphorus limitations, etc., the growth of the cells and the death of the cells more or less take place at similar rates. And so you reach what is known as the stationary phase. So for example, when they're saying over here that takes place under nitrogen and phosphate limiting conditions after growth has ceased, they're really talking about this portion. The final is that when your nutrients have got badly depleted, then your cells will keep dying and more cells are not going to get created, and that's the death phase. That's when
Excuse me, sir. Sorry to
yeah,
interrupt you. So please could you repeat the part for stationary phase?
yeah. So what happens is that, you see, obviously when I'm doing this, I'm consuming up nutrients, right? Or I might deliberately want to not provide certain nutrients because I want to promote the promotion of the secondary metabolites. I'm not just per se interested in the growth of microbes. I'm interested in a product. So I'll see under what conditions my product quantity is maximized. And that may not be beneficial for the growth of the microbe. So effectively, the stationary phase is that when there is some kind of a depletion of some of the essential nutrients required for the growth of the bacteria, and not for the production of metabolites, but for the growth of for the cell division. So then what happens is that the rate of growth and the rate of death become comparable. And so, this is the stationary phase. This is log of numbers of bacteria. So this is just got to do with the numbers. It's got nothing to do with the amount of your metabolite which I seek to produce. And then, of course, when nutrients have got badly depleted, then of course death will overtake growth. and then there will be a slow decline, and this is the death phase. Is that clear?
Yes, sir. Thank you, sir.
That's very important, which means that when I'm trying to produce these things, I cannot just look at growth of the microbe, right? And cell division. I've seen people, they'll put it in the microscope, they'll say, oh, my cells are multiplied, but that may not be what is of interest to you. You'll have to analyze at each of these stages and see at which point I'm getting a maximum. Naturally, if I've got very few cells, obviously I'll produce less. But even after I've got a large amount of cells, I may still produce less. So I need to have a look at that. So the carbon source, and then sometimes there could be certain additives which are present in your maybe in your water or other in your feedstock, which you might have to contain because some of them could have an inhibiting effect. Sometimes they have a positive accelerating effect, and sometimes they have an inhibiting effect. Like for example, here in citric acid case, they have to actually reduce the concentrations of iron and manganese to about a ppm or less. So they will need to bind it up, which they might be able to do by things like adding cyanide and forming ferrocyanide and complexing up the iron. That could be a way of doing it. In the case of citric acid production, you can see that you require high dissolved oxygen concentration. Okay, can anyone tell me why? Why do
So
I
the
need oxygen?
biochemical oxygen demand will be high.
No, but why? Why do I need oxygen?
So growth of the
Biochemical
bacteria.
oxygen demand is a separate thing. That is about the organics which are present. I'm talking about you have to purge oxygen.
So growth of the bacteria, sir.
Not really. I mean, yes, to some extent. Well, citric acid, you're starting with sugars. Citric acid is an oxidized product, right? There are carboxylic acid groups over here, three of them. So obviously it's an oxidation reaction which is taking place. So I need an oxidant, and my oxidant is my oxygen. Is it clear?
Yes, sir.
And contrast that with ethanol. I'm taking a sugar, and over there I'm actually having to defunctionalize. And when I make ethanol, I have to actually reduce the oxidation state, okay? Because it's just CH3, CH2OH. Whereas my sugar has every carbon has an OH. So there, what happens is that the oxygen which the bacteria requires for its metabolism, or the yeast or whatever, those things are really being extracted from the sugar itself. So there you are really taking out the oxygens, you are defunctionalizing the sugars, whereas here I need to oxidize the sugars to be able to produce citric acid. So the two situations are completely different. You need a high sugar concentration in this process. This is very interesting. You actually need a very low pH. In fact, I'm just trying to see, there are certain schemes where I'm just trying to see where you can naturally gain from a low pH. And this is the temperature. Now, what I'm talking about over here is a solution-based fermentation. But the Japanese, they have come up with solid state fermentation. They actually can take cassava, which is very rich in starch, and they actually introduce bugs and all into that cassava and do the fermentation in the solid state. It's a different way of doing things. Now, there is another very important concept which is known as batch or fed batch. What happens is that sometimes you might find that you are doing a fermentation with something. I need that. But that thing itself is an inhibitor. I'm fermenting it, that's all right, but it's also inhibitor in my fermentation process. So what I then want to do is that I don't want to have a large excess of my feed. I will continuously keep feeding the feed as it is getting consumed. So I'll have a kind of a steady state in terms of the availability of my feed. Alternatively, it could also be that my product is inhibiting my fermentation, in which case I must remove my product as it is being formed. So these are all the nuances of the process. So that's what all these things are talking about. Everything that I've explained. One more thing. Remember, when you're dealing with bacteria, fungus, these are things which, if you subject them to excessive agitation, their cell walls and all can break. So what you have to do is that you have to be extremely careful when you are dealing with those, and make sure that, of course, you need some agitation, but you must do the agitation in an extremely controlled manner. That's what you have to do. Now, that's not all. You have done your fermentation, you have got your product, then comes recovery. For example, in the case of citric acid, most acids, carboxylic acids, when you have calcium salts of carboxylic acid, they're highly insoluble. So in this particular case, what they do is they just add lime and it will form calcium citrate and it will precipitate out. Once I precipitate it out, all the rest of my stuff which I added for my fermentation, including my feed and things, all of it just remain in my aqueous phase. And then what I do is I take the calcium citrate and I can re-acidify it with sulfuric acid. It will again form calcium sulfate, gypsum, and it will give me citric acid. I take out the citric acid, and if it is dark in color or something, I might bleach it or I might recrystallize it, and I'll end up with citric acid. So you can see the nuances of, depending on how I do a process, starting with the same feedstock, sugarcane juice or molasses, I can end up with different outcomes. And so that's what makes these bioprocesses and fermentations extremely tricky, but also gives great opportunities of making a wide variety of products, starting with the same feedstock.